So in the previous video, we were mainly looking at this particular example, right? We're trying to compute the revenue for the total revenue for each of the day through the week from Monday to Thursday, right? And what we have found is that we can actually represent this particular problem as a vector multiplying a matrix, right? And we were able to actually implement this a vector matrix multiplication with this nested loop in Matlab, right? To make the problem slightly more complicated, let's look at a kind of different example, right? The example may appear different, but in fact they are actually both of them actually involve matrix vector multiplication. So, and this example is taken from this particular publication. It's written by an economicist. So the problem description is like this. We have three people, right? P1, P2, and P3. They want to buy some a collection of items: rolls, buns, cakes, and bread. Right? Those four items, right? Four different items, and each of the person will need those four items for different quantities. Right? So, for example, the person P1 is gonna need 6 rolls, 5 buns, 3 cakes, and 1 bread. But person P2 are gonna need 3 rolls, 6 buns, and 2 cakes and 2 bread. So different person will require different amount of those, different number of those different items, right? So you can actually organize the quantities, the demanded quantities of each of the person into this kind of a table, right? And then the row number is for different person, right? P1, P2, and P3. And then the column number is the demand for different kind of items for the different person, right? So the first column is the row demand for the row for P1, P2, and P3. And then the second column is the demand for buns for P1, P2, and P3. And then you have two shops. You have two different shops, S1 and S2. And then in these two different shops, the different items are going to have different prices. Right? So in shop 1, S1, the roll is going to cost $1.5 per roll, and then the bun is $2 per bun, and then the cake is $5 per cake, and then the bread is $16 per bread. But the price in shop 2 for the same items is going to be $1 for the roll, $2.5 for the bun, and then $4.5 for the cake, and then $17 for the bread. So the goal is to actually find for the different person, P1, P2, and P3, find the best store, find the best shop to purchase his or her required items with and pay as little as possible, right? You wanna pay as little as possible, right? So for those kind of demanded quantities and for the given prices, we want to find the cheapest option between S1 and S2. So how can we actually do that, right? So how do we actually find the total amount of money to pay for total amount of cost for each of the person, right? So suppose we wanna buy all the items for P1 inside of the shop 1, S1. So what's going to be the calculation, right? So P1 is going to require 6 rolls. So 6 roll times 1.5, right? And then he's going to need 5 buns. So 5 times 2, right? And then it's going to require 3 cakes, 3 times 5, right? And then 1 bread, 1 times 16. So you add those up, you get the total amount of cost for P1 inside of the shop 1, for the first person inside of the first shop, right? It's basically just this kind of a element-wise or component-wise multiplication and then summation, right? And this is exactly what we actually did when we actually we're actually doing this kind of a matrix vector matrix multiplication. So this row was doing a component-wise multiplication with these three numbers in the first column, right? We get the total amount, right? And then doing the multiplication with this row with the second column, right? Component-wise multiplication and then summation, we get the total price for the second column, right? And here we are pretty much doing the same thing. So in order to actually get the total cost for P1 inside of shop 1, we're doing a row, a component-wise multiplication of this row with this column, and then a summation, right? So if we want to find the total cost for P1 inside of the second shop, all we have to do is to do this kind of component-wise multiplication of this row with the second column in this table, right? And then do a summation. Then we get the total price or total cost for P1 inside of the second shop, right? And then all we have to do is to sort of do a comparison, to do a comparison of the two different costs and find the shop with the minimum cost, right? So let's see how we can actually do that in Matlab, right? So this is still the script from our last example, right? Let's write a new section. So again, let's first define the prices matrix, right? You have to make sure that the row, bun, cake, and bread is in the same order. So the ordering of the rows must be identical to the ordering of the columns in this particular table, right? It's a row, bun, cake, and bread. Row, bun, cake, and bread. So if you switch any of the two rows in this particular table, you have to sort of switch the corresponding columns in this particular table. You have to make sure that the column and the row are indeed consistent between these two tables in order for the calculation to be correct, actually, right? So now let's take a look at how we can actually do this, right? So prices, it's 1.5, 1 semicolon, to, and then switch to a different row, right? 2.5 switch, right? And then 5, 4.5 switch, and then 16, 17 switch. That's our prices vector, prices matrix. And then we're gonna need a matrix to represent these demanded quantities, right? This is 4 rows, 2 columns, right? And then this one is actually 3 rows, 4 columns, right? Quantities. Let's still call it quantities. Then it's 6, 5, 3, 1. Switch to a different row, and then 3, 6, 2, 2. Switch to a different row, and then 3, 4, 3, 1. So if we just want to run this code, let's comment out. Let's suppress all the output here, but show the matrix here. Right. And then let's sort of make sure that our input is indeed correct. So it's 1.5, 2, 5, 16, right? And then it's 1, 2.5, 4.5, 17, right? And then the quantities is 633, 564, 323, and then 121, right? So it looks like we have entered the numbers correctly. Right. So how do we actually compute the cost for the person P1 at the two different shops, right? At the two different shops. So so if we actually look at this particular nested loop, so how do we actually adapt it so that we can compute the costs for person P1 in the two different shops, right? Suppose let's still compute it by let's still write the expressions by hand, right? So quantities For the first person, it's actually the first row, right? It's actually the first row. It's actually the first row. So the row index is kind of fixed, right? So the row index is kind of fixed. And then all we have to do is to actually iterate through all the column indexes. It goes from like 1 to 4, right? It's either 1 or 2 or 3 or 4, right? So let's call it IC. That's the column index, right? And then multiply with what? Multiply with the prices. The prices, say in the first shop, right? Prices. The first shop is what? The first shop is actually the first column in this prices matrix, right? The first column means the second input must be 1, right? And then the row ID, right? So row ID must go from like 1 to 4, right? And this row ID is actually the same as the column ID here, right? So you want to multiply this, the first column of this row with the first row of the first column, and then you want to multiply the second column of the first row, right, with the second row of the first column, right, and then the third column on the first row to the third row of the first column, right, and then the fourth column of the first row to the fourth row of the first column, right. So if you are using IC to index as a column index into the quantities matrix, and then you have to use the same index to retrieve the corresponding ID in the prices vector, right? And then you have to do a accumulation or do a summation of this particular multiplication in order to actually get the total cost for the first column, right? So suppose let's call it. Let's call the result of the summation. Let's call the result of the summation. Let's just call it cost S1, P1 S1, right? And then all we have to do is to actually loop through 1 to 4, right? And then cost P1 S1 is just equal to cost P1 S1 plus this one. And then all we have to do is to iterate through this. And then we can look at the cost P1 S1. So cost P1 S1 is $50, right? So cost P1 S1 is $50. So for person P1, if he or she chooses to actually buy all his or her items in shop S1, then the total cost is going to be $50. And then what's going to be the total cost if person P1 chooses to purchase all the items inside of the shop S2, right? So all we have to do is to actually change these prices matrix. Here we are just using the first column. That's all the prices inside of shop S1, right? So if we want to compute if we want to sort of if person P1 wants to purchase all the items in shop S2, all we have to do is to actually change this first column to second column, right? And then that's S2. And then we can display S2 also, right? That's $49, right? So if the person P1 chooses to actually purchase all the items inside of shop S2, then the price is going to be $49. That's like $1 cheaper than purchasing all the items from shop S1, right? So in principle, the person P1 should choose to buy all the items inside of shop S2, right? So for person P1, shop S2 is actually the better option, right? The problem is just how we can actually formalize this particular calculation, right? How can we actually formalize this particular calculation? So here we are basically changing the variable names, changing cost P1 S1 to cost P2 S2, right? And then manually change the column index, right? The column index for prices, right? So let's just like the previous example, let's try to actually add to wrap this particular loop inside of another loop that's gonna allow us to actually loop through all the different shops, right? The two different shops. Right? We have just two options for the shops, right? Either shop 1 or shop 2, right? And then compute the total price or total cost for person P1. So let's get rid of this part, and then let's just initialize cost P1 to just the 2 zeros, right? And then we can just display cost P1, right? And then in this case we can do another loop, right? Maybe not a good idea to use IR here. Maybe it's a good idea to use I shop, right? I shop goes from 1 to 2, right? And then end. I shop. Shop, right? And then I shop. Yes. And then in the end we want to display cost P1, right? So cost P1 is going to be 50, 49, right? So for the first shop, the total cost for P1 is $50, and then for the second shop, S2, the total cost is going to be for P1 is going to be $49. So based upon this calculation, for person P1, the better choice is shop 2, S2, right? But don't forget, if we let's just indent the code correctly. But don't forget, it's not just the one person, right? We actually have like 3 persons. We have P1, P2, and P3, and each of them are going to require different quantities for different items, right? So how do we actually convert that into a Matlab code, right? How do we actually do that? So in order to so this nested loop, this 2-level for loop, is for just computing one row of this particular matrix, right? So all we have to do is to actually repeat the same calculation for like 3 times, and each time with a different person, right? And then what exactly needs to be changed for each of the different person, right? Different person are just different rows in this quantities matrix, right? So when we actually index into the quantities matrix, all we have to do is to actually change this 1 to range from 1 to 3, right? So that's all we need to change in order to actually compute the cost for the different people, right? So let's change that. Let's try to change that, right? So the first thing we're gonna do is to actually try to actually so this is cost for just one person, P1, right? Suppose we have a second person for cost P2. We can do the same thing, right? 0 and 0. And then the cost for P3 is just still going to be another 0, 0, right? So if that's the case, we can just combine these 3 row vectors with just the zeros into like a 1 matrix, right? So costs is going to equal to zeros, and then it's just going to be 3 rows and 2 columns, right? So in this case, we don't really need to actually use 3 variables. We just use 1 variable, right? And this variable is going to have 3 rows, and each row is for the cost of 1 person, right? So the first thing we can do is to actually replace these 3 lines with just this 1 line here, right? And then this 1 comes from the first person, right? First person P1, right? But what I was saying is that all we have to do is to actually change this fixed row number 1 into a loop index, that goes from like 1 to 3, right? So let's add another level of loop. So for, let's just call it IR, row index, right? Goes from 1 to 3, right? And then let's just make sure that the n actually matches, right? And then make sure that the indentation is correct. Right. And then costs. We want to display the costs. So now cost P1 must be replaced with the correct row number inside of the costs matrix, right? It's not, so cost P1 is the cost for the first row, right? So IR, that's, so when IR equals to 1, that's the costs for person P1, right? And then when IR equals to 2, that's the second row, that's for the cost for the second person, right? And then we can do the same thing here. Costs, IR, iShop. Right? And then quantities, 1 is for just the first person, the first row, right? But now we are looping through, we're actually iterating through the different rows. So for the first iteration, IR equals to 1, right? But for the second iteration, IR is supposed to be equal to 2, right? So we need to actually change this fixed 1 to IR. And that's actually all the changes we need to do in order to actually compute the costs for the 3 different people inside of these 2 different shops, basically. Right. And then let's do the calculation. Right. And then that's the cost. So for person P1, in the first shop the cost is 50. In the second shop the cost is 49. So person P1 should choose the second shop. Right. And then for person P2, in the first shop the total cost is $58.5. And then in the second shop the total cost is 61. Right. So for person P2 the better choice is shop S1. And then for person P3, the total cost is $43.5 in both shops, shop S1 and shop S2. So either shop works for person P3, right? It's the cost is identical. So first person P3 can choose either S1 or S2 as for purchasing all the items, right? And we have implemented this particular calculation by using this kind of a three level nested loops, right? And if we want to sort of use Matlab's internal multiplication matrix multiplication capability, all we have to do, so this kind of 3 nested for loops can be replaced just by a very simple function call. So it's basically just quantities multiply prices, right? If we just do this calculation, then the result will be identical to costs, which is obtained by using these 3 nested for loops, right? Let's just run it, and you can see they are indeed identical, right? The results are exactly the same, right? So internally, Matlab actually knows that this is a matrix, and this is another matrix. And when you are actually connecting 2 matrices using the star, using the multiplication, Matlab is automatically going to apply this kind of a matrix multiplication rule between 2 matrices. And internally, Matlab is going to replace this multiplication with this kind of a nested for loops, but it's implemented in a much more efficient way. Right. So that's how this particular calculation is actually carried out. Right. But in order to actually understand how matrix multiplication is carried out internally, and also how to use this kind of nested for loops, right? This example actually also demonstrates how nested for loops can be used in Matlab, right? Let's try to actually convert. Let's try to convert this particular code, this particular nested for loop, into a Matlab function. So for now, everything is done in just inside of a script, right? Let's try to actually convert it into a function, into a Matlab function, right? But in order to actually convert the whole calculation into a function, we need to understand the ranges, right? So for now, all those ranges, 1 to 3, 1 to 2, 1 to 4, those numbers are hard-coded, right? Suppose we have like not 3 people, but 4 people, or 5 people, or 10 people, that kind of thing. Not just 2 shops, but like 10 shops or something, right? Do we really have to sort of modify this kind of a number or the range numbers by hand, right? If we have to do that, then it's kind of tedious and also error prone, right? And it's not kind of generally applicable to any kind of different kinds of data set, right? So in order to actually make our function sort of generally applicable, what we have to do is to actually obtain those range numbers automatically inside of our function, basically, inside of a function, right? So how are we going to do that? How are we going to do that, right? But let's take a look at this particular specific example and see if we can actually come up with some kind of general rules about the range, or about the row and column numbers, right? So if we look at the quantities matrix, it's 4 different columns, right, and then 3 different rows, right? So in linear algebra, people often say it's a 3 by 4. 3 by 4. So in linear algebra, this is incorrect code. This is not a code. This is actually just the text, right? So the quantities matrix is 3 rows and 4 columns. And in linear algebra, people often say this is a 3 by 4 matrix. 3 is the row number, and 4 is the column number, right? And then the process matrix has 4 different rows and 2 columns. So in linear algebra, people often say it's 4 by 2. Right? Do you see the convention? It's a row number followed by the word by, and then followed by the column number, the number of columns, basically. Right? So one of the things that you might have noticed is that this 4 is exactly the same as this 4 here, right? And they must be equal to each other. Otherwise, this kind of component-wise multiplication is not going to work, right? You remember, we multiply 6 with 1.5, 5 with 2, 3 with 5, and then 1 with 16, right? Suppose you have like one more column here, right? Say it's cheese, right? Cheese, amount of cheese, right? Say 3 cheeses or something, right? And then you don't have an item for cheese in the price column, right? And then that's not going to work. You have 3 cheeses, but you don't have a price for it, right? Then the multiplication is not going to work. This kind of component-wise multiplication is not going to work. So the matrix that's in the front, which is the quantities here, and its column number, which is 4 here, must be identical to the matrix that's following, right? It must be identical to the row number for the matrix that's following it, right? So this is sort of the column number of the first matrix, that's the quantity matrix, must be equal to the row number of the second matrix, which is the prices matrix, right? Otherwise, the multiplication, component-wise multiplication, is not going to work, right? So when we actually try to write a function to do this kind of a multiplication, we have to sort of do this kind of check to make sure that the 2 input matrices do follow this particular pattern, right? So the row number and the column number do have to be consistent between these 2 matrices, right? And a second thing that we have to sort of notice is that what's actually the costs matrix, right? What's actually the result of the costs matrix? What's actually the dimension of the costs matrix, right? The dimension of the cost matrix is what? Is 3 by 2, right? It's 3 by 2. It's 3 by 2, right? It's 3 rows and 2 columns. And then what exactly is the kind of pattern that you have detected, right? So the row number of the result multiplication matrix 3 actually equals to the row number of the first matrix of the quantity matrix here, right? And then the column number of the costs matrix is what? Is actually the column number of the second matrix. That's the prices matrix here, right? Right. And this kind of pattern is also general. It's also can also be generalized, right? So basically, by just looking at the size and the dimension, the shape, basically the shape of the two input matrices, you can figure out what's actually the size of the resulting matrix that you have to sort of return, right? And now let's try to actually convert what we have observed into a solid function, right? Solid MATLAB function. So make our idea more kind of concrete, to materialize our sort of observations and concepts, right? So now let's try to create a MATLAB function. Try to create a MATLAB function instead of a matrix, right? Instead of a script. So for some reason my screen is kind of not exactly aligned very well, but it's okay. Let's just click on new and then function, create a new function, and then the out args. Let's just call it costs or something, right? Costs, and then the input args are gonna be two matrices, right? Quantities and then prices, right? Quantities and prices. The first one is quantities, and then the second one is prices. And then let's change the function name from untitled2 to like my mat mal, right? My matrix multiplication. So let's change the command line. Matrix multiplication. So quantities first matrix in front of star multiplication, right? And then prices, that's the second matrix after the star multiplication, right? And then costs result of the matrix multiplication. Right. And then let's just copy this piece of code over here, and then later on we're gonna fix the dimensions, right? Let's cut it. Control X to cut it, and then paste it over. Control V to paste it over. Right. So for now all the dimensions are fixed, right? But our observation was that we can actually obtain those dimensions dynamically based upon the shape of the two input matrices, right? Then what's going to be the shape of the two input matrices? There's a MATLAB intrinsic function that's called size, and this size function is going to return the row number, the number of rows, and the number of columns of the input matrix. So quantities, if we give quantities this matrix to the size function as the input, then it's going to return a matrix as output, right? And then this matrix are going to have two elements in it. The first element is actually the number of rows of this quantities matrix. Let's just call it QR, right? And then the second output is going to be the total number of columns of this particular matrix, right? Let's just call it QC. And then we can do the same thing for the prices vector, prices matrix. prices, and then it's gonna have two outputs. Let's call it PR and PC. Right. So now we have obtained the entire the shape of the two input matrices. Right. The first observation that we made was that the number of columns of the first matrix QC must equal to the number of rows of the second matrix PR. Right. So which means that the QC must equal to PR for our calculation to actually continue. Otherwise, we are going to report an error message. Right. So if QC not equal to PR, so in Matlab, this is not equal to. Oh no, it's not. This is not equal to. Right. This wiggle followed by the equal sign with no space separating them. The whole thing is called not equal. Right. If QC is not equal to PR, we're going to report an error message. Input matrix dimensions don't match. Do not match. Right, and then we're gonna just do an AND here. Right, so once it reaches this particular error message, then this function is gonna automatically sort of stop. Right, it's not gonna sort of continue executing. So only when this condition is false, then this error message is going to be sort of skipped. This display of the error message is going to be skipped. So it's going to go to the end right away, and then it's just going to keep executing. Right. Once it gets to the error message, then the execution of the function is going to be stopped. Right. But if you actually prefer, you can also do this thing, else. Right. Else means that this conditional is evaluated to false, which means that QC is indeed equal to QR, right? And then you can just wrap everything that's underneath it inside of the else block, and then put an AND to close this if block. So if as soon as I typed AND, MATLAB editor actually displays this AND is actually paired with this particular if, right? Either way is fine. Right? But if you actually enclose everything inside of this else block, you have to sort of pay attention to the indentation of the lines, right? One of the things I think that might be able to do is to actually automatically indent it, right? So suppose I select this part and then right click, smart indent, right? Smart indent. So smart indent is going to allow me to actually it's going to allow me to fix the indentation automatically. Right. So that's to account for our first observation, right? So QC must equal to PR, otherwise the calculation, the matrix multiplication is not going to work, right? And our second observation is what? Our second observation is that the dimension of the output matrix, the costs, is actually fixed by the dimensions of the two input matrices, right? So the total number of rows of the costs matrix should be identical to the total number of rows of the quantities, the first matrix. That's QR, right? So now let's replace these three with QR, right? And don't forget, we also have these three here, right? That's sort of inside of this kind of a range operator, right? We are using three. We can also replace these three with QR also, right? And then the column number of the output matrix must equal to the column number of the second matrix, right? That's the process. That's PC here, right? So that's PC. So we're replacing 2 with PC here, right? And we also have another 2 here, right? We also have another 2 here. We can also replace it with PC here, right? Yeah. And then the next thing that we have to sort of make sure is that is that we replace this 4, right? So what exactly is this 4? What exactly is this 4? Right, this number 4. How do we actually replace this hardwired 4 with the correct correct variable, right? With the correct variable, right? So how many times we have to sort of iterate in here is actually the row number. The row number of the first, no, not the row number. It's actually the column number of the first matrix and the row number of the second matrix, right? Where we actually got this 4, right? If we look at our example, let's go back to our example. Where exactly did we actually get the 4, right? Where exactly did we actually get the 4? Right? We did this innermost loop with IC goes from 1 to 4 is to account for this summation, right? So after this kind of component-wise multiplication, we have to do a summation, and this 4 is actually account for that kind of this for loop with the range goes from 1 to 4. Actually allows us to do this kind of summation, right? So if you look at IC is indexed into what? IC is actually the column index into the quantities matrix, right? That's the column index. And then IC is also used as the row index into the prices vector, right? So we did this 6 multiply 1.45 plus 5 multiply 2 plus 3 multiply 5 and then plus 1 multiply 16, right? And this kind of summation, the pluses are accounted for by this particular for loop, right? And then the number 4 is exactly the column number of the first matrix, which happens to be equal to the row number of the second matrix, right? Not happens to be, it must be equal to. All right. If it's not equal to if they are not equal to each other, then this condition is going to be true, and then it's going to display this error message. So this 4 is what? This 4 is actually, you can put either QC or PR here. It doesn't really matter, right? Because QC must equal to PR in order for this thing to execute, right? And then let's save this particular function. Matlab, let's just save it. Right. And then we can just go back to our experiment, and then to our script, and then call the costs equals to, call the function matlab, and then give the quantities at the first input, and then prices as the second input. Right. Call it function, and then let's just run it. Right, the result is still correct, which means our function is implemented correctly, right? And that's how we actually do matrix multiplications, right? We have implemented our own matrix multiplication routines, right? But let's try it in a different way. So suppose I want to switch the order of the prices and quantities, right? Suppose I give the two inputs in the wrong order. Suppose I do that, right? See if we can still get the same result. And it's telling me that no, it's giving us an error message, and the error message that's being displayed is exactly the error message that we actually put in there, right? Put in there. The input matrix dimensions do not match. Right? Why it's not matching? Why it's not matching, right? So prices now becomes the first matrix, and then quantities becomes the second matrix. And prices is what? Prices is a 4 row. It's a 4 by 2, right? It's 4 by 2. And then the second matrix quantities is what? It's 3 by 4. Right? The inner dimension, these two dimensions, the column number of the first matrix must match the row number of the second matrix. right? So it actually violates our first sort of observed pattern, right? So that's why it's not going to work. It's not going to work, and it's going to display the error message correctly, right? So matrix multiplication is kind of is not commutable. So if we just multiply two numbers, say 2 multiplied 3, that's 6, right? 3 multiplied 2, that's also 6, right? So this kind of number multiplication is commutable. Commutable means that if you switch the order of the two numbers before and after the multiplication operator, the result is the same, right? But for matrix multiplications, it's not the same thing. It's not the same thing, right? So the same is true not just for our own matrix multiplication function, but also for Matlab's matrix multiplication symbol. This star here, right? So if we do quantities multiply prices, that's gonna work. But if we do prices multiply quantities, that's gonna give us inner matrix dimensions must agree error message, right? So it's basically just stating the same kind of a thing here in a different way. Input matrix dimensions do not match. It's pretty much the same kind of a it's actually telling you similar kind of a problem basically, right? Similar kind of problem, right? So matrix multiplications are not commutable in general. They are not in general commutable, right? Unless the two matrices are kind of a square matrices, right? But if they are square matrices, the result won't still be matched, right? So suppose we want to generate, so A equals to, we want to generate a random matrix 3 by 3, right? And then B is another random matrix 3 by 3, 2 by 3, right? And then C1 is going to equal to A multiplied B. So this time the multiplication is going to work, and then it's going to return this kind of a square matrix 3 by 3, right? And then C2 is going to equal to B multiply A. Again, it's going to work. It's not going to display any kind of error message. But if you compare C1 with C2, are they identical? They are completely different, right? They are completely different. Even though it's not spitting out an error message, but the result of the multiplication for A multiply B and the result of multiplication for B multiply A are entirely different, right? So matrix multiplication are not really commutable in general, right? And we need to actually keep that in mind when we actually write our Matlab codes, right? We have to sort of make sure that the dimensions are indeed correct, right? They indeed match. The inner dimensions must match in order for the calculation to work. And we have to sort of bear in mind that the ordering of the two matrices are very important, right? It's not commutable. Yeah, let's stop this video here, and next time we're gonna look at some different applications of linear algebra.